All right, welcome everyone. Today we're kicking off our journey into the very heart of computing. We're going to pull back the curtain on one of the most powerful and often invisible concepts in all of technology: algorithms. These are the secret engines that run our modern world, and by the end of our session today, you'll have a much clearer picture of why they are so absolutely critical.
So, have you ever stopped to wonder what the secret recipe is behind, well, everything? What's the magic that powers your phone, your search engine, or even the mind-boggling logistics of a global company? Well, it's not magic. There's an invisible logic at play, a specific set of instructions that makes it all work. And that's exactly what we're here to understand.
So here's the game plan for our first lecture. First, we'll nail down a really clear definition of what an algorithm even is. Then, we'll jump into the real world and see just how huge their impact is. After that, we'll dig into a super important idea: why a smarter algorithm is often way better than just a faster computer. And finally, we'll peek into the future and talk about some of the really tough problems that computer scientists are wrestling with right now.
Okay, let's dive right in. First things first, what exactly is an algorithm anyway?
Now, the formal definition sounds a little academic, but the idea is actually incredibly simple. At its core, an algorithm is just a well-defined procedure. Think of it like a recipe. Seriously, you start with your ingredients, that's the input, you follow a very precise set of steps, that's the procedure, and you end up with a delicious meal. That's your output.
And here's that exact idea in action. Our input is just a jumbled mess of numbers. The algorithm, our recipe in this case, is a sorting procedure. It gets to work, follows its steps, and voila! The output is that same list of numbers, but now it's perfectly ordered from smallest to largest. This simple flow, input, process, output, is the basic building block of every single algorithm.
Okay, so we've got the definition down. But this isn't just some abstract concept for sorting numbers. These recipes are everywhere, and they have a massive, tangible impact on pretty much every part of our modern lives.
I mean, just look at this. The applications are all over the map. Algorithms were absolutely essential for mapping our DNA in the Human Genome Project. They're the reason you can safely buy things online. They optimize how factories and shipping companies work. And of course, they're what finds you the fastest route when you use your GPS.
You know, every single time you click a link or send an email, there are algorithms working behind the scenes, managing a colossal amount of data. They're like the world's best air traffic controllers, but for information, finding the most efficient path for data to zip around the globe in a fraction of a second.
And what about when you buy something online? Ever wonder how your credit card number stays safe? Well, you can thank some really sophisticated numerical algorithms. They form the backbone of public key cryptography, creating a secure tunnel that shields your private information from anyone trying to snoop.
The scale of some of these problems is just mind-boggling. The Human Genome Project had to identify and sequence 3 billion chemical base pairs. Trying to store and analyze that amount of data would be literally impossible without some very clever algorithms designed specifically to handle these enormous biological databases. So, we've seen what algorithms do, but how they do it makes a world of difference. And this brings us to maybe the most important lesson you'll learn today. It's not always about having the fastest, most powerful machine. A lot of the time, the recipe you choose is far more important than the computer you run it on. So let's compare two different recipes for that same sorting problem. On one side, we have insertion sort. Its running time grows quadratically. Basically, as you add more data, the time it takes gets longer and longer very, very quickly. But on the other side, we have merge sort. Its running time grows much more slowly, much more gracefully. The key here is that as the problem gets bigger, insertion sort's time requirement just explodes, while merge sort stays manageable. Okay, to really hammer this point home, let's set up a little competition. In one corner, we've got a supercomputer, a real beast, but it's running that less efficient insertion sort. And in the other corner, a regular old PC, but it's using the smarter merge sort algorithm.
Now just look at these numbers. The supercomputer is 1,000 times faster than the PC, but it's stuck with the bad algorithm. The job is to sort 10 million numbers. And the result? It's just astonishing. The supercomputer takes over 5.5 hours. The humble little PC, using the smarter recipe, finishes the same job in under 20 minutes.
Let that sink in. The slower machine, just because it had the better algorithm, was over 17 times faster. This is the power of algorithmic efficiency. It can completely blow raw computing power out of the water.
So, this all leads to a really fascinating question.
We've seen how powerful the right algorithm can be. But are there limits? Are there problems that algorithms just can't solve efficiently?
And the short answer is, well, no. At least not as far as we know. There's this wild category of problems in computer science known as NP-complete. You can think of them as puzzles where, if someone gives you an answer, it's super easy to check if they're right. But finding that answer in the first place, it's incredibly, brutally hard. And for these problems, nobody has ever discovered an efficient algorithm.
A classic example is the traveling salesman problem. Just imagine a delivery driver who needs to visit, say, 50 cities and get back home, all while traveling the shortest possible distance. As you add more cities, the number of possible routes just explodes into insanity. Even with the fastest computer imaginable, finding the one single perfect route is practically impossible. So for problems like this, we have to use algorithms that find pretty good answers, good enough answers, very quickly.
And here's the mystery that keeps computer scientists up at night. No one has ever found an efficient algorithm for these NP-complete problems, but no one has ever been able to prove that one can't exist. It remains one of the biggest, most tantalizing, unsolved questions in the entire field.
So, the crucial point to take away from all this is simple. Algorithms aren't just some abstract piece of code. They are a technology, every bit as important to a system's performance as the physical computer chips it runs on. The overall performance you get depends on both of them working together.
And that's exactly why we're here. Understanding this stuff is what's so empowering. Having a solid foundation in algorithms is what separates people who can just get a program to work from people who can get a program to work brilliantly and efficiently. It's a key that unlocks so much more potential. So I'll leave you with this final thought for today. The next time your GPS finds that perfect shortcut, or you stream a movie without any buffering, or you buy something securely online, just take a second to think about those elegant, invisible procedures humming away in the background. Think about the algorithms that make it all possible.